Hey, everybody, and welcome to another episode of Software Defined Everything, the podcast for smart world systems. Today, I'm joined by Rajiv Joshi. He's a principal solutions architect here at RTI. And today, I want to set the stage. We're going to be talking about edge computing, specifically the phrase, the edge is the new cloud. Let's talk about what this really means, why does it matter, and how it's changing the way developers build connected systems. That being said, I'd like to introduce Rajiv Joshi. Thanks for joining the podcast.
Oh, absolutely. You're welcome. Thanks.
Well, the edge is the new cloud. This is a phrase you hear kind of buzzed around in the industry. What does that phrase mean to you, Rajiv?
Well, that's a great question, right? So it means a number of different things. To me, I think of it as an evolution of the computing architecture, right? So in some ways, it depends on your perspective, what that means to you. And I've kind of seen it from both ends. So if you are sort of more in the cloud computing side of things and quite familiar with the cloud, think of a cloud sort of now starting to reach out into the cyber physical world, which is really the world of connected, machines, the world of compute or intelligence connected with hardware. And that hardware could be sensors or it could be actuators, or think of eyes and ears and the limbs, right? So you can actually operate on the real world and you can move things around or you can act on something and make that happen. So that's one way to think about it. Another way to think about this is that the edge itself, is getting more compute, and so it's sort of extending into the cloud. So because people are starting to connect more and more devices and connecting them to the cloud infrastructure to be able to use those resources. So yeah, so I think it's a great sort of new evolution of the compute architecture where you can have many more new type of applications that you didn't have before. It opens up really exciting new possibilities.
Right. For our audience, how would you specifically define the edge when it comes to real world deployments? How we would see the edge
Yeah,
in the cloud
yeah,
implemented in the
yeah.
real world?
So one of the things that I've been involved in a lot of industry and consortia efforts and the Industrial Internet of Things, Industrial IoT Consortium of the IIC. I was participating in the edge computing working group, and then also was leading the connectivity task group there. And we define the edge as essentially the cyber physical boundary, right? So it's a very crisp and clear and unambiguous definition. In other words, where your compute system, your cyber system meets the physical world, right? And that boundary, you can think of that as the edge. Right now, for a lot of people, they think of this as a continuum because, again, that boundary is really kind of a little bit in the perception of the person looking at it, right? So, for somebody coming from a cloud perspective, it's basically the device that's connected, right? From the perspective of a device, that boundary could be the local sort of compute node. Let's say that you're operating in a mine or agricultural equipment, right? And then maybe you have machines that are plowing the field or trucks that are doing mining operations, right? They might connect to a computer on that mine site, and you might say that is the edge, right? Or if this, let's say, tractors plowing a field, they might be connecting to some local sort of compute on the farm. You might say that's the edge, and then from the perspective of that edge device, you might be connecting to maybe yet another compute infrastructure that might still be somewhat local. And eventually you might get to what people think of as cloud, like public cloud, like Amazon or Azure or, the Google Cloud and other things, right? So it's really a continuum. And those are different kind of deployments we see today, right? So we see that machine device going directly to the cloud, like, for example, fleet management with cars, right? You might have a vehicle that might be connecting directly to the cloud that's being managed by, let's say, the fleet management operator, right? Or monitoring sort of information about that, you know, about that vehicle or device. Or you might have something going sort of to a local. So that's the continuum. People have used the word fog for this as well when people think of this as a continuum. And if you look at the teleoperations world, there's been this concept of mech has been around for years as well. So yeah, edge is very crisply defined, but there's a little bit of leeway in terms of, where you're coming from again.
I'm a little curious, going back to your agriculture example, say a tractor plowing through a field, the edge doesn't need to be on the tractor itself. It could just be in the proximity of the field. It doesn't need to be in the device itself. Is that what we're talking about?
You could think of it that way, where, right, the tractor might be doing its stuff and it's connected, and maybe the connectivity is intermittent, right? So you're not always connected, but you don't need full connectivity to be plowing the field, right? Because a lot of the stuff can happen autonomously, or somebody could be operating it if it's not an autonomous machine. But then when you have connectivity, it might want to share data, and that data could be all kinds of data, right? Including just, you know, what I've done so far, or what kind of, my the vital signs are for the device itself, and so on, right? And that so that might just be going to a local sort of compute device, and you might say that is the edge, right? Some people will call the tractor the edge, right? So it really depends on the perspective, and some people will say, well, that local sort of compute that's running where the tractor is moving the data to, conceptually is a cloud. And so some people like to define cloud as, and we had very interesting debates in the IIC on this topic, right? Because some people will say, well, I'm deploying all the cloud technologies, I'm applying all the 12 design the design principles of cloud computing. So, well, it's cloud, right? But you can do that because that's just compute infrastructure, right? So some people think of cloud as, it has to be in a data center. Some people think of cloud closer to sort of the edge, but then the edge of the edge is that physical boundary, right? So that's the tractor, because the tractor is the device that's interacting with the field, right? It's the equipment that's actually interacting with the physical world, right? So that's the cyber physical boundary. And that's why I said, it's very crisply defined in my mind. But then, the edge to cloud is also a continuum. And a lot of people will argue that as well. So,
It's funny that there's still a big debate about some of these things and defining what words mean what, when the edge isn't really something new. It's been around for a long time, actually. But I wanted to ask you, what's changed? Why are industries now moving into more compute and intelligence over to the edge?
yeah. So two things fundamentally have changed. And it's really been an evolution, but you get to sort of a critical mass and a point, and then you suddenly start seeing transformation. And those two sort of things are connectivity and compute, right? So when it comes to connectivity, now you're starting to see connectivity everywhere, right? Almost, everything has like a Wi-Fi, or like, it's a little bit want to spend more money, then you might have a LTE chip, a cellular chip, right? So, but machine, small devices and at very low cost points can now start to talk and communicate with adjacent devices or adjacent compute, wherever that might be. And so that has led to, this ability to leverage what is not possible with the resources you have on that device. That's really at the physical boundaries, at the cyber physical boundary, right? So, and that connectivity has allowed devices and compute to exchange, data, right? And that data sharing unlocks new potential, right? And obviously we're always innovating, so we're always thinking of new ways of, hey, what else can I do with this data, right? Like I have this lawn mowing robot, let's say, and it's mowed my lawn. Well, what else can I do with this, right? Or like, I have one tractor, it's plowed a piece of the, my land. Well, if I have two tractors, like, can I sort of optimize this operation somehow, right? Or if I had a big sort of, lawn to mow and I had three robots working, right? Can they sort of optimize, right? So they can talk and do stuff, right? So connectivity changes things, right? Because it gives you new ways of doing things. The other thing that has happened is compute, right? Because now, because all the compute doesn't have to be on board, you can go to compute resources that might be available adjacent to these devices, right? So, and then you can leverage that, right? So that allows you to do a lot more things. People are starting to put now, I mean, of course, who hasn't heard of AI and Gen AI? And AI isn't new. It's been around since, I was in grad school and even before, I was, even when I was in high school and stuff, right? So it's not a new concept, but it's sort of gone through this sort of, the computer has evolved, right? So like one of the things I'll tell you is, probably everybody has heard of a neural net, right? And I was just, looking in through some old boxes of, and I tend to save my books, and I tend to sort of, hold on to my pieces of work. And I found my bachelor's thesis, and it was like neural network based pattern classifier. So I was building like a neural network in hardware. Of course, it was like a tiny, tiny,
Right.
tiny microcontroller and all of that, right? So that was undergraduate, right? But now, of course, the scale at which people are building these things and the amount of parameters these things have is huge, right? So, you can put a supercomputer in your pocket, right? That's your cell phone, right? You can do so the amount of compute you can do has gone up like exponentially, and continue to go up, right? So that's created new opportunities. So now if you think of connectivity, being able to exchange data, right? And then think about compute that can do something interesting with that data and make decisions and make them fast, then suddenly you have this whole new sort of palette to work with and new applications you can create, right? So I think that's what's changed, what's different. And so it feels like a step function, but it's really not. It's been a gradual evolution over time.
It seems like the massive exchange of data, one, and the evolving compute that we have nowadays, those two paired together open up tons of possibilities and new applications. But how can those two paired together make an existing application more efficient? Say, we'll go back to the agriculture tractor. How can those two things that weren't quite evolved back in the day make something exponentially more efficient today?
Yeah, absolutely. So imagine like you have a farm, right? And you've got different crops going in. You have lots of tractors, and they are working on different parts of the farm. Well, could they coordinate and collaborate to make sure that you get the job done in half a day, or half the time that you would normally take? Because now they can say, well, I'm sort of optimally planning my work plan, right? So you kind of got different plots of land assigned that they're working on, and then they could say, well, I've done this part and I'm done till here. And you could reroute and replan, and you could kind of collect that statistics. You can also then have other kind of equipment that needs to then do follow through work. So you can completely optimize the way you work, essentially, right? So, that's a huge opportunity, right? So you can do things that would have otherwise required manual scheduling. Somebody would have to come there and would have to then say, okay, this is done. I'm going to put this here, and I'm going to sort of, all of that can be automated because now these can share data in real time, or, when they have connectivity, they can do that. Right. And then there's compute available also locally or in the cloud, depending on, where you choose to do these things, where you can make decisions, right? So some decisions get made locally, and then others that maybe require more resources get made maybe further away, right? And sort of more in the cloud.
Right. With the availability of all the data plus the compute, it's limitless on what you can achieve in terms of this system.
Exactly. Exactly. Yeah.
So I'd like to take a quick moment to debunk common misconceptions regarding the edge. That being said, what is a common misconception when it does come to the edge?
Yeah, that's a great one. So it was a few years ago. I remember when cloud computing was fairly new and people were starting to connect things. And at that time, I was, we were just ramping up in the IIC, and I was, leading as the chair of the connectivity task group, the work on the IICF, the Industrial Internet Connectivity Framework. And there were people who would come up, and I remember like people say, well, now I don't need any on-device computation. I can just push everything to the cloud, right? So this idea that oh, I can now have completely dumb devices and I can push everything to the cloud. So that's sort of a misconception, because the reality is that it depends on what you're doing. And then, and if you're doing things that where timing matters and where bad things can happen because you don't have backend connectivity, then you need to do local compute still, right? So yes, you can push some of the things to the cloud, but not everything necessarily, right? Especially if it's anything so that has to do with autonomy or anything to do with, and I'll give you an example in a moment. But so that's been one common misperception. The other is that the edge replaces the cloud, right? So that's, I think, also sometimes we see that people think, well, I don't need the cloud anymore. I can do everything on the edge. Well, I mean, people have been doing things on the edge. I think, like I said, the new thing is now they can be connected. And that's the opportunity, and they complement each other, right? That's the right way to think of it. It's not like the edge replaces the cloud, or the cloud replaces the edge, or now I can do everything in the cloud, or now I can do everything in the edge, right?
Right.
So that's
And that makes the phrase "the edge is the new cloud" a bit misleading because one isn't replacing the other. They're more of just complementing each other, and each one's doing its respective role to make a more efficient system.
yeah. And the way I think I'd like us to think about this is, and this is why I thought the title was particularly intriguing and interesting, because if you are coming from a cloud perspective, you should be thinking the cloud sort of now sort of seeping into the edge, right? And it can reach, and like it can get its fingers into the edge, the as close to the edge as possible, or appropriate, or possible. And also another way to think of it, if you are like coming from a very edge perspective, is that the edge can now seep into the cloud in the sense that it can leverage the resource in the cloud, right? So it's kind of like that, I see. And yeah. So they're really complementary things. Yeah.
Let's talk a little bit about where the edge is most needed now, where people see the most immediate use for it. There's tons of smart connected systems today, but which one of those use cases require the edge to cloud as of right now in a more immediate sense that you could see?
There's actually all kinds of new use cases coming. Right? So the obvious ones, I think, when people initially started, when we were starting out in the IIC, looking at this, people were thinking really just monitoring, right? And monitoring is like, okay, I'll give you a slightly different example this time. Like, okay, I have my washing machine. I've got, I need to sort of change, some, does it need repair, right? Or I have my vehicle, or I have like some other equipment, and you know, before it's due for maintenance, I can monitor its performance over time, and I can sort of predict a little bit of what the condition of that equipment is. And based on that, it's called conditional monitoring. I can sort of automatically place an order saying, okay, here's the replacement part for you, right? Before you actually, before the thing breaks, right? And so the idea there was, okay, we are saving time, right? We are, based on monitoring and data we are collecting, we can save that time from, okay, observing the failure to replacing the part, and the sort of the delays in that process because there's inventory management, other things, right? So you can sort of be more predictive about that, and be more efficient. From there, and that use case is still there, but use cases like, I am going to be able, I'm operating this vehicle on the road, let's say, and I want to be able to, you know, use some advanced algorithms. So there are people trying this, or I'm working on this tractor, and then if I have access to some compute resources, I might ask for some planning to be done at a very supervisory high level, right? Where I might get a high level plan and a guidance and a direction as to what I should be doing next, right? Because I don't have the local resources available in terms of compute. And that decision, if it's available to me, I can use to improve my behavior and performance. So if it's not available, then I'll continue to do the way I do things, right? So now it's starting to get a little bit more real time, and it's starting to become more operational, right? Rather than just maintenance and prediction, it's starting to be part of the operation of that equipment, machine, device, asset, as different people like to call it, on that cyber physical boundary, right? So you can improve that, right? Or if I have, like I was saying, collaboration, right? If I have multiple pieces of equipment and collaboratively, they have to team up to complete a task, like that was a tractor example I had, right? If they can exchange information, and they can then have some reach back into more resources, which might be cloud-based, they can leverage those, and they can now sort of, this cloud-based sort of supervisor could be collecting data from 10 different tractors who are working on this farm. They understand what it's doing. And then it's saying, well, now I'm going to reschedule you this way because this is the more optimal thing to do now, right? And each tractor then starts to do its own thing. So by themselves, they don't have the resources or the visibility to make that sort of global decision. But then some supervisor can make that decision, right? Because it's seeing sort of the state of everything. And that's a more real-time operation, right? So this is like, what happens during the course of a day versus sending a new part when it's getting worn out, right? Or about to break. Right?
Right.
So those are more real-time, I suppose, type of applications.
You mentioned autonomous vehicles, and this is an application where real time decisions are so important. In this example, when you have maybe a bicycle that appears in front of a car and it needs to brake in real time, or something appears in the road, those types of decisions would be made at the edge as opposed to going to the cloud, right? Because they need to be decided on immediately.
Yeah, yeah, absolutely. And that's what we would call real-time, right? So and this goes back to the point I was saying earlier, like not everything can be pushed to the cloud, right? There are some things that have to be made locally, even when you have no external connectivity available, right? And you need enough compute resources to do that, because if you can't make those decisions, then bad things happen. Usually, like people die, or there's damage of property and other things, right? So, like, kind of, so the question is, what is real time, right? And one of the first demos, it kind of goes back to grad school days. It was for NASA and was a teleoperation demo, right? So we had a five-finger robot hand, right? And we had instrumented that. So as you sort of do some operation, you could have, you would wear a glove essentially, and this hand would essentially mimic your operation, right? So you could essentially say, okay, I'm going to grab this object and put it here, right? And then the hand would actually go grab that object and put it here. And this was really for space operations type of, this was like being funded by NASA. One of the first things I learned was how important latency was, right? Latency is, how fast an update shows up, right? But even more important than latency is how predictable that latency is, right? And that's called jitter, right? Like, is there a lot of variability, or is that pretty consistent, right? It always takes me like, 10 milliseconds or 20 milliseconds to get that data update. All right. So you need that kind of thing. Now, the decision of like somebody, a biker, a bicycle comes in front of the car is like that, right? You need to collect that data, right? You've got your cameras and lidars and radars and other, and then from that sensor suite, you are doing some processing that needs to happen on board, because, it takes too much time to send it outside the vehicle, right? So that compute is local. And then once that compute is done, you have to make a decision locally, right? Now, the policy may be coming from cloud as to what kind of high level policy you apply, right? And the policy could change, but will change at a different rate, right? So you might have a policy decision coming from the backend or the cloud that might influence the high level sort of behavior and the decision paths it might take, but that detection and reaction has to happen in real time on the vehicle, right? And that requires like predictability and real time operation there.
At RTI, we offer RTI Connext, which, seems like a bespoke solution for something like this. But aside from the real time application and nature of RTI Connext, what other factors make it such a good fit for edge to cloud applications?
Well, RTI Connext is built on a standard. It's completely standard based, and that standard is called DDS, Data Distribution Service. And that standard is something we have analyzed very extensively in the IIC as well, and kind of, and IIC was a collaboration of industry leading experts, and kind of judged that standard as really the only standard that meets, it's designed from ground up for real time operation and real time. So I think the question often comes up, what is real time, right? And real time is about operating on the now, on the current state, right? Whatever that now is. Now, the now may be different for, different applications and use cases and contexts, but the now in the case of a bicycle in front of a car is like, if, milliseconds, right?
Right.
Because you have physics, right? And that physics, your momentum, your vehicle moving, right? You need to brake, you have a braking distance, right? I mean, there's laws of physics you have to respect, and they kind of give you those constraints, right? So RTI Connext is designed. So, DDS is the standard that's sort of designed for real-time applications. And then RTI Connext is that leading implementation of that real time, right? So from the very beginning, we have always focused on how do we minimize the latency end to end of data delivery, and then how do we make sure that the jitter is extremely low, right? So it's very predictable, right? So, real time requires predictable operation, right? And that's what RTI Connext is designed to do. So, initially we started out focusing on just sort of edge devices and, compute, especially, you know, outside of devices was sort of, and cloud computing was still sort of in its early days because, when did the standard get the first spec came out in 2004, right? And that's when we released the RTI Connect's first version. And then, cloud computing, I think, was still not a term people used back then. We used to call it the enterprise. All right. And as those technologies have evolved, we have added more things, right? So we have added now WAN connectivity, which allows you to connect to the backend, right? Infrastructure. So just like, we are on this call, or, people use Zoom or Microsoft Teams or, Google Meets or FaceTime or whatever, right? It's completely seamless, right? You don't think about, you know, how that end-to-end call gets established and how that session gets established, and it feels all happening in the now, right? Of or a conversation, right? Well, it's the same thing, except now it's a conversation between machines. And RTI Connect is designed to be able to do that in that real time, in that context of real time, right? In that context of latency and jitter, and be able to do that seamlessly, to be able to connect devices and equipment and, components on a local area network, on a wide area network, across different zones and across different sort of regions. So, that's where now we're spanning sort of this end to end. We're calling this like connects to anywhere, right? So RTI connects to anywhere, from, just on your edge or just on your cloud or between edge and the cloud. So kind of the entire spectrum, and kind of also be able to do this continuum as well.
Right. We talk about RTI Connect or DDS as a concept. It's important to also think of the concept of data centricity and how this makes everything work. How do you see the concept of data centricity evolving? How can the evolution of data centricity contribute to the evolution of edge to cloud end to end systems?
Absolutely. Right. So the core idea of data centricity is very simple, right? Data is a primary asset in your system, right? And data comes first and then applications. Data is stable, applications come and go, right? We also call this data-oriented architecture. And I also chair the AVCC software portability group, and we've been focused on, how do you build software architectures for autonomy, especially when it comes to autonomous vehicle architectures, all the way from, level 2 to 5. And how do you do that in a way that's portable, that's interoperable, and that's also composable, right? So that's been our focus. And we just published the data-oriented architecture for computing, for, autonomous computing, and we've kind of gone in a lot of detail on this concept of data-oriented architecture, data-centric architecture, and define that. And at its heart is this idea that if you are doing something, you don't really care, where your inputs come from. You just simply say, okay, this is what I need. This is the data I need. I'm just simply declaring that. And and then you're doing your thing, whatever processing you need to do on that data. And then you are simply then saying, this is what I'm offering. This is my output. And I don't care about where it goes. Something in between takes care of who needs what, when, where, right? So you're simply offering that data and making it available, right? And you don't care where it goes, right? So that thing in the middle, also called middleware, we also call it the Connect data bus, takes care of getting the right data at the right place at the right time. And it completely abstracts away the idea of, you know, the connectivity at an abstract level. Is just, make sure that the data gets to where it needs to be, whether it's everything is local on the same host, on the same computer, right? If it's going between different computers but connected over high-speed fabrics, or or shared memory, right? Or or if it's going off board, or like off vehicle, right, to another, or off tractor, or to another sort of location, right? Off site, essentially, right, to a remote location. And then so it's completely seamless, right? So we think of this as like this data sort of continuum where we just get the right data to the right place at the right time. So that's I think what's one of the things that we have been kind of really sort of focusing on, and that's how data centry is evolving. So as a concept, it's very simple, right? The way I described it: data is a primary asset, applications come and go. Data is what will survive because data is based on essentially the physics of the domain. Or there's there's so many ways you can model position and location, and acceleration and velocity and so on, right? So those are fundamental concepts of physics, right? And when you are building things for the cyber physical world, those are the concepts that govern the operational aspects, right? And then you can build lots of different type of applications around that. You can build different policies around that in terms of decision making. You can, right? So the important thing is then being able to realize this in a way that's completely seamless, and that's where I think we have tried to really work hard and continue to just make sure that this idea of data as a primary asset and data anywhere and everywhere at any time sort of holds. And that's not easy. That's a hard problem, right? It sounds easy, but if you sort of focus on that fundamental idea, then you can build all kinds of interesting things.
I'd like to slightly pivot and enter the inevitable part of any current podcast these days, and that is talking about AI and how it's used. We hear about it every day, and AI is evolving every day, often in a consumer way, ChatGPT and text building and software building AI tools. However, in the industry of physical AI for end-to-end big distributed systems, how do you see the edge taking on AI workloads for their systems? And how are developers going to have to think differently when developing and building these types of systems?
So there's many ways to think of this, right? One is, AI is essentially a tool, right? So, and as a tool, we are, we like to call ourselves the AI enablement company, right? So first of all, if you think about, and you may have heard this phrase, data is the new oil, right? If I don't know if you've heard it, but
I
I
have,
keep
yeah.
hearing it all the time. And so AI feeds on data, right? And so in AI, like you can almost think of, two very distinct aspects. So one is training and the other is inference, right? Training is basically, a lot of the times, AI is fairly broad, right? And my PhD work and thesis work was in the field of AI. I was doing sensor fusion, but AI has evolved. And back then we used to think of, neural networks as one sort of approach to AI, and symbolic computation as another type of an approach, right? And so AI is fairly broad. I think a lot of the time these days when people talk about AI, they're talking about Gen AI really, and large language models, because that's sort of the new and exciting thing. And in that context, those models have allowed us to, provide intelligent assistance for developers building these kind of systems, right? So that's sort of the third aspect I wanted to bring in, right? So there's, how do you build these systems? What data do they need, right? And then how do you get the data to the right place at the right time, right? So if you think of applications of AI where somebody is building some AI, and this AI needs to be connected to sensors and actuators, because those are the eyes and ears and the limbs of that system, and the AI is the brain, if you think of it that way, right? That's a very nice way to think about it, right? So that AI needs that type of physical connection, and that's where you know, you need data flow, right? You need data distribution. You need this concept of a data-oriented, data-centric approach where you're focusing on the data, and the AI could also change, right? Because you could change the AI model, right? And there are lots of different models available, right? So, but it's the same data inputs and the same data outputs, right? So enabling that, right? That's one aspect. If you're thinking of training AI, right, and learning by example, that's the training aspect. Again, you need data, right? You need data coming in real time. You need data going out, and essentially, closing that loop so you can train the AI model. And oftentimes now what we are seeing is people are running out of data, especially when it comes to cyber physical systems. So people are sort of leaning towards simulation, right? And they're trying to use physics-based simulations to essentially then train the AI models, right? And so in that training process, again, you need to be able to emulate or simulate the physical world, right? So again, you need enough of a model so you can do things in a timely way, and you need data distribution again, because these can get very complex, and then you need to feed that to the AI. So that's the training side of it, right? Okay, so that's just how do you build the AI, right? Right, and then how do you use the AI? You need the data, right? That's the oil aspect. But then there's another aspect, with in building these systems, with the language models available today, can we accelerate the way people develop, right? Like, who hasn't used ChatGPT or one of the other large language models, right? Probably almost everybody has heard of ChatGPT or Gemini or Claude or any of these, right? So when you are using these models are really good at sort of learning all the knowledge that they've been trained on, and then giving reasonably decent answers, right? Reasonably good answers. And of course, people are continuing to innovate and improve that. And the techniques where the more context you provide, the more precise answers you can get, right? So what we have done, and we've just released this Connext AI, right? We've trained a large language model, right, with everything, so it understands everything about RTI Connext, right? So they can act as an advisory. It can answer your questions. It can help you design the data-centric, data-oriented architectures and systems, and it can help you leverage RTI Connext in a very effective and efficient way, right? So you can become very productive very quickly, right? So that's the third aspect of AI. I think that all this touches. So to me, this is just like, it's a very natural evolution. It's just, it all fits together nicely, right? So there's design, there's inference, and then of course training, and all the three aspects. Yeah. And simulation, I think, would be the other one. Yeah.
I think that segues nicely into my last question as we wind down here, which is, if you had to give one piece of advice to a system architect designing for the edge today, and say this is a developer using a software framework like Connext, what would that be?
I would say make data your primary asset and think in a data centric or data oriented way, where you think of data as state that you manipulate, and as a software component that you're creating, whether it's AI, whatever AI that my component might be using. Think of what you need in a declarative fashion, what you offer in a declarative fashion, and then build your system architecture around that idea, right? And that allows you to evolve the system in a way that's resilient, that's extremely high performance, that's extremely scalable, that's extremely reliable, and can continue to sort of survive, even though individual applications and components may change over time, which they will. I guarantee you that, right? So that would be the most valuable thing to keep in mind. Keep in mind, RTI Connext doesn't tell you how to build a system, right? so so just like C++ doesn't tell you necessarily how to do object-oriented design,
Right.
but it's very well suited for object-oriented design, but you don't have to, right? In the same way, DDS is extremely, and RTI Connext is completely sort of built around the idea of supporting data centricity and data-oriented architecture, but you can apply it just as a messaging technology, right? Or so just use it in the way it's meant to be used, or you get the most value out of it, I think.
Right. Fantastic. Rajiv, where could people learn more or find some of the resources connected to what we were talking to today?
Yeah, I think we are more developer oriented. I think there are two places I would say. One is, the RTI community, community.rti.com is the URL. And that will also link you to the GitHub RTI community, which is fairly large. And there's a lot of stuff in there, from examples to use cases to sort of, you can get something up and running very quickly. So and also the developer page on rti.com is also quite nice place to get started with, because if you've never played with this technology before, then this is a good place to start as well. But yeah, I would just refer you to the community page, the RTI community, community.rti.com. Probably a good starting point. We'll probably have links to everything else.
Right. Awesome. Rajiv, thank you so much for joining the podcast today. You're extremely insightful, and I know I learned a lot, so thank you very much for joining.
Thanks, Steven. Thanks for having me.
All right, thank you.